Good morning, everyone. I'm Xue Chen, a graduate student from Hehai University. It is a great honor to be here to share my recent progress, and the title is the simulation study on the influence of downstream structural joint surface defects on cavitation in adjacent areas. And my presentation is divided into 4 parts. First is the background. As civil and hydraulic engineering have advanced, the number of high dams in mountain gorges has significantly increased, exemplified by the Derina Dam in Turkey, the Cavit Dam in India, and the Jinpingwang hydropower station in China. With increasing dam heights, challenges in flood discharge and energy dissipation have faced challenging. As we know, cavitation occurs when local pressure drops to the saturated vapor pressure, and the phenomenon is common in aerospace and turbo machinery. Previous studies have summarized the damage patterns of concrete under cavitation and demonstrated that the surface irregularities will induce cavitation. Despite extensive research on hydraulic concrete cavitation, studies on cavitation damage near transverse joints are rare. These joints often run across the entire dam section, and if filling materials are damaged, uneven regions may appear. Cavitation erosion occurs near the joints firstly and then spreads further, just as the figures on the PowerPoint. So the overflow surface of the dam section needs frequent maintenance. After flood discharge in summer every year, repairs are needed and the cost is almost unaffordable. This paper uses numerical simulations to study cavitation distribution near transverse joints, providing theoretical support for dam design and maintenance. And the next part is governing equations and computational setting. We consider 2 fluids, liquid water and water vapor, and we assume that both phases are homogeneous. We employed the volume of fluid method to handle phase change between these two fluids. The method defined a variable alpha to track the interface between the different phases, and it represents the volume fraction. Because only the liquid water and the water vapor are present, we have the alpha L plus alpha V equals 1, and the phase transport equations between the phases can be represented by these two equations. And the right of the equations is mass transfer rate. We can combine 2 phase transport equations to get the continuity equation, and the momentum equation does not change because multi-phase model. There are 3 cavitation models in open form: the Quantz model, the Merkel model, and the Xing-Zhao model. And I believe you have heard them in the technical section multi-phase flow. The Quantz model and the Merkel model are empirical model. They simplify the mass transfer rate calculations, and they can be used in less detailed simulation. Xing-Zhao model balances the complexity and applicability, and making it suitable for a wide range of things. Hence, we choose this model. When local pressure reaches saturation pressure, bubbles grow, and when the pressure exceeds saturation pressure, bubbles collapse. Each state is represented by 1 equation. The cavitation model reflects the relationship between the mass transfer rate and the pressure. By using these 2 equations, the mass transfer rate can be calculated and can be substituted into the phase transfer equations to solve them. Now we talk about the turbulence model. The shear stress transport K omega model is particularly effective. It combines the accuracy of the standard K omega model in the narrow region with the robustness of the K epsilon model in the far-field flow. This makes it suitable for handling turbulence separation, reattachment, and high strain rate flows. the red front part is the blending function f1. When it takes a value of 1 of the near wall region, it is the k omega flow. It is a k omega model. When it takes a value of 0, it is a Cavitson model. The computational domain is the transverse joint on the overflow surface. Based on engineering experience, damage to transverse joint filling material often occurs discontinuously. So in this study, we assume there are 2 defects on a single transverse joint separated by a certain distance, and the water flows from the left to right, with the area displayed in blue. In the above figure is the structural joint defects. Cavitation will appear when the water flow velocity reaches 20 meters per second. For dams with a head exceeding the 200 meters, even the 300 meters, the flow velocity can reach up to 50 meters per second. So the inlet flow velocity is set to this range. The width of transverse joints often ranges from a few millimeters to centimeters. So we set it to the 6 millimeters, 10 millimeters, 14 millimeters, and 20 millimeters. And the other variables were also set to the range. Our simulation was conducted using the interface change form solver. Now we talk about the results. By observing the cavitation counter, we can identify 2 primary causes of cavitation around the structural joint. And this PowerPoint is the first one. It shows the generation of cavity. In the joint, water flow encounters obstructions at the end of the defect areas, causing the flow to move either upward or downward. A portion of water moves upward and creates a high velocity region on the overflow surface. This area is prone to cavitation, and its mechanism is similar to the seal. When the cavity is forming, they move downstream with the flow. At the same time, the cavity also spreads laterally, thus erosion the overflow surface around the joint. And this PowerPoint is the second. A portion of water obstructed by filling material moves downward and then flows backward along the bottom, and subsequently moves upward, merging with the main flow. This creates a recirculating flow within the structural joint, forming a vortex. The low pressure at the center of this vortex can induce cavitation. The cavity then travels along the flow to the overflow surface, where it is no longer confined by the walls and spread laterally in both directions. As shown in the left graph, at a flow velocity of 20 meters per second, there is a slight presence of vapor due to the sudden change in cross-section at the end of the defect. The right 2 figures are time-advantaged water vapor volume fraction counter maps at 20 meters per second and 40 meters per second. And we can see only blue color in the red circles. Means that no cavitation occurs. But when the flow velocity increases, and the cavitation begins to appear within the joint. When the flow velocity further increases, the cavitation intensity in the second defect exceeds that at the same position of the first one. If we take the logarithm of time-advantaged water vapor volume fraction to draw a graph, we get lines near the joint, and we get these 4 figures. We can fit it with a linear function. As the flow velocity increases, the lines becomes more gradual, indicating that the cavitation decays more slowly and the cavitation regions becomes larger. Moreover, with the increase in flow velocity, the cavitation intensity near the edges of the joint slightly increases, and it is not obvious. As illustrated in the in the first figure, different joint widths show similar vapor volume fraction, and we can see the middle 2 points of the different colors overlap, which indicates little impact of joint width on cavitation intensity at the end of the computational domain. And the other two figures show the effect of the length of defects and the distance between two defect areas. In a word, these two variables have little impact on the time advantage vapor volume fraction. Based on above analysis, an empirical model can be established. The time advantage vapor volume fraction varies significantly at different positions. So the logarithm of the time of the values are fitted. A linear fit is performed. These results are shown on the right table. In this table, A represents the slope and B represents the intercept. It should be noted that the linear model only represents the distribution pattern of cavitation within a certain distance from the joint. The regions far away from the joint exhibit different patterns. However, since cavitation mainly occurs near the structural joint, the empirical model in this study focuses on the distribution pattern within this range. The fitting results are displayed at the bottom. It can be observed with the velocity and the width increasing. The lines become more gradual. The line becomes and is an exponential function. When the flow velocity increases, the intercept of the intercept increases monotonically, and the impact of the flow velocity on the intercept can be described using an exponential function. However, the effect of joint width is more complex. The time advantage vapor volume fraction at the edge of a 10 millimeters wide joint is greater than that of the 20 millimeters wide one, creating a peak in the function along the width axis. So we use a parabolic fit to fit it. Now we can draw some conclusions. This study simulates the cavitation phenomenon around the transverse joint of an overflow demonstration, and we can draw some conclusions. Cavitation around the structural joint is primarily caused by abrupt cross-sectional changes at the end of the defect areas and the vortex flow within the joint. The flow velocity is the most significant factor affecting the cavitation intensity. Moreover, an empirical model was used to establish a relationship between the time advantage vapor volume fraction and the flow velocity and the joint width. And there are some shortcomings that need to be discussed. Through the impact of structural joint cavitation on the surrounding flow surface in this paper does not exceed 20 millimeters. The unevenness of the flow surface caused by this impact will lead to further development of cavitation erosion of the surrounding flow surface. And in this study, only one section of the transverse joints was studied. And in actual engineering, the transverse joint runs across the entire dam section and with a length of up to hundreds of meters. The multiplied damages on the transverse joint were not simulated in this paper. That is all my presentation today. Thank you for your listening. And